Hi, everyone. We're going to talk about lecture 5, which is basically on more runtime stuff that we saw from last lecture. We're also going to talk about sorting. We're going to start with our n squared sorts. Most of you probably have seen these in the past, but there's kind of a reason for why we're doing all of this. You'll see soon. So we're going to talk this lecture about big O, big theta, big omega, which we've talked about big O before, but big theta and big omega are pretty important too. I don't know why theta and omega are switched here. I should fix that. And then we're going to go and do a little bit of practice. From there, we're going to talk about sorting. Why do we even bother studying it in this class? And then go over insertion sort, selection sort, and quick sort. Right, so there's one sort that's missing in these slides. I've edited these slides a couple of different times, so this is slightly out of date, but you can imagine we're going to study 3 sorts, not 2 today. What will the quiz on Thursday be on? It's going to be on runtime and big O. So I'll talk more about that during the break. For now, you can just assume that it's on the stuff from last week as well as the beginning of this week. So if you remember the definition of big O, this was a lot of math. This is maybe scary for some of you, but remember, don't shut down. Just power through and know that you can learn this stuff. All right. So don't just immediately give up it just because you see a bunch of math symbols on the screen. Big O is saying that given a function f and a function g, we say that f is in big O of g. That's how you read that. When f of n is less than or equal to k times g of n as n approaches infinity, where we have some constant k, which means that k is just some sort of number, right? If f is in g of if f is in big O of g, we can say that g is an upper bound of f, and also that f grows no faster than g. Now, looking at this page, you probably already forget what this definition means. So let's go and recall what we looked at last week, right? So we had two functions, two mathematical functions, right? We're not talking about code right now. We're just talking about math. And we had f of n is equal to 3n plus 4. And then we had g of n is equal to n plus 2. And we asked, is f in O of g, right? And just to recall, we're really saying here is f in the bag or the set of all functions that look like g on a graph, right? So like we have this function g, we plot it on a graph. There are a lot of other functions that kind of look like what g looks like on a graph, and we're asking, is f one of those functions? Right? That's literally how you should think about big O, because big O is all about charting the progression of a function, the behavior of a function as n increases on a graph, right? Because it just shows you how slow or how fast this function will grow as time goes on, or as the size of the input increases. So in this case, we have n plus 2 and then 3n plus 4 graphed on this little graph here on the right. And we're going to try to figure out how to prove that f is in big O of g. I'm going to give you all 20 seconds. This is just review, right? This is literally the example we had on Monday or Tuesday of last week. 20 seconds. How do I prove that f is in big O of g here? Type it into chat. Don't hit enter, and then we'll review it together. All right, go ahead. What do you think? We have to find a constant. We have to multiply a constant. Most people are saying find a constant, right? So essentially, people are saying that if we look for some k, right, that can multiply g, that we can multiply with g, and that resulting line, that resulting function is greater than this red line, which represents f, then we would be good, okay? So in this case, what's a k that we could pick? Go ahead and type in chat if you have a constant that you want to use. What's your favorite constant here? Right. And hopefully you all are like thinking for yourself and then not just copying what everyone else is typing in chat. I mean, you can if you want, but even if you're confused and coming up with the wrong answer, I'd much rather see that than have everyone just spew the right answer and just copy from everyone else, right? This is why I have everyone not type in their answer beforehand and have everyone just wait for a second, because I want to see what you all pick. And it's okay to be wrong, because the whole point of this class is to learn. So if you don't make mistakes, you're never going to learn. So in this case, if we, for example, say k is equal to 3, I'll do this in a easier to read color. If k is equal to 3, then we know that then 3 times g is essentially 3 in 3 in plus 6. I think that's how math works, right? So we've come up with a new line, a new function, by taking this 3 and multiplying it by what g was. If g was n plus 2, then we have 3n plus 6. We get to draw this line, which starts at 6 and goes up kind of like this. This line is blue. Okay, that's fine. We'll just make this blue as well. There we go. And you can see that it's bigger than f, this red line, 3n plus 4, for all time, right? As n increases and becomes bigger and bigger, this line will always be on top. This blue line will always be on top of the red line. And therefore, the answer to this question is yes, right? So hopefully this doesn't seem too scary. This is essentially a review from what we talked about before. If you feel a little bit uncomfortable about this still, please go back and review lecture from last week. The videos are already posted on the course website. I will always encourage everyone to go back and watch the videos. People say that when they review the videos, they do better in the course, and data, obviously backs that up. So what I mean is, like, these two videos from last week, you just go to csc4520.org, click through to the videos here, and then you should be able to review them, right? And one other thing we wanted to ask is G in O of F? So we reverse the positions of F and G in this case. I'll give you another 20 seconds. How would you answer this one? What K would you pick? Again, I want you to think for yourself. Don't just copy what everyone else is typing. Don't type in the answer right now. Just think about it for yourself. Get ready to type in the answer. And then when I say, everyone will hit enter with their answer, right? Again, the goal of this is to actually learn something in lecture, not just to listen to me drone on and talk monotonously. All right, so in this case, go ahead, punch in your answer now. Is the answer here yes? Okay, some people are a little bit confused. That's totally great. That's totally fine. I'm thankful that you told me. And then some people are feeling good. They're saying that K should be like 1, K should be... All right, so we got a few questions. So let's go over this in detail then, right? So this is a saying that is G, this line here on the bottom, this blue line, let me just clear everything up real quick. This blue line here, can we say that it's in O of F, which is this red line? In other words, can we say that F in this case is bigger than G for all values, right? So this is a little bit confusing because now it says F and G, like this is reversed, right? So we need to just reverse these terms. If you're looking at the blue segment here, it might be a little bit confusing because this covers if F is in O of G, but if we want to go and think about the opposite, then we just need to replace these with the corresponding values. So if G is in colors, if G is in O of F, then what we need is that figure out a K such that K times F is greater than G for all n as n approaches infinity. In other words, do we have to multiply this red line by any number that we can think of, any constant number, such that it's always bigger than the blue line? Yes or no? Do we have to do any multiplication? Not really, right? But we know that since the red line is above the blue line for all values as n approaches infinity, then we can say to the second question, yes as well. Okay, so again, just a review, when we are trying to compare two mathematical functions and we're trying to say that one is in big O of the other, what we're saying is, given their lines on the graph, can we make the second function be bigger than the first function for all values across the graph as n approaches infinity? So the answer the reason why people are typing no in chat right now is because they're saying, oh, I don't actually have to multiply this red line by some number, right? Because it's already bigger than the blue line for all values. All right, so we're already good. We don't actually have to do anything. In other words, you can say that k is equal to 1, and that would have been fine. Pick k is equal to 1 here. All right. So if you are still having trouble with this, there's a bit of practice online, and we'll talk about that in a bit. But this is definitely something really important. We're going to cover this on the quiz and definitely on the exam. Obviously, for the quiz, it's a little bit lower stakes. You can work with other people in the room to understand what's going on and at least get the right answer. But you are responsible for trying to understand this. So if you get confused, feel free to either ask me questions or, go ahead and uh, make some office hours, book some office hours with me. I'm happy to explain it to you one-on-one, right? The course website has your ability to schedule office hours with basically me and 3 of the TAs. You can schedule an appointment anytime you'd like, and I'm available on Wednesdays and Fridays. The other TAs are way more available, and they have a lot of time on their hands. They're happy to help, right? For example, Jared has a lot of time, especially in the mornings, right? So if you are stuck on anything and you want someone to help you out and not make you feel bad for not knowing something, these TAs are here to help. I've made sure that they're kind, and that's like the number one thing. They're kind, and they got an A plus in my class last semester. Those were the 2 requirements. All right. So if, for those of you who are still like a little bit confused, please come to office hours. Please review the videos. We're happy to help. All right, so let's keep going. How does this all relate to runtime? We'll talk about it in a bit. That's a great question. So let's go ahead and just continue with the math for now. And then in a bit, we'll talk about the runtime. Okay. So big omega in this case is another notation that you'll need to know. Omega is a way of describing functions in their growth, such that given an f and a g, right, 2 mathematical functions still, that f is in omega of g, which is the same as saying g is in O of f. So it's actually the exact second question that we asked last slide. And that's essentially saying that g needs to be smaller than or equal to some k times f as in approaches infinity, right, for some positive constant k. Okay. Now, you might not understand what this means in this context, so we'll look at an example shortly. But basically, if we say if f is in omega of g, we can say that g is a lower bound of f, and also that f grows no slower than g. Okay. Again, blue slide just means you need to memorize it for now, and then hopefully over time, we're working through examples, the meaning will come afterwards. But we're going to keep looking. One last definition, right? If you understood big O, if you feel good about big O, these definitions shouldn't actually be that scary. Big theta is essentially tight bound. So it's saying that both f is in O of g and f is in omega of g are true at the same time. In other words, that we have some k here multiplied by g, which is less than or equal to f. But then we also have that f being less than or equal to k, another k times g as n approaches infinity. All right. So we can say that f is in theta of g is a tight bound. All right. I don't know if I said O or omega before, but I meant theta all this time. F is in theta of g is the same as saying f is in O of g and f is in omega of g at the same time. Okay. So let's go back to our example. All right. We have this. We know that f is in O of g based on what we talked about before. Now, we also said that g is in O of f. What else can we say about f and g? All right, so can we say, there's 2 questions I want to ask here. Can we say that f is in omega of g? Can we say f is in theta of g? All right, those are 2 questions I want to ask. Go ahead and take some time to think about them. I'll give you 20 seconds based on the definitions we had before. Remember, omega just means, i.e., is g in O of f? And then this is, i.e., is f in O of g and is f in omega of g, which, you're about to answer anyways, right? So that should help. I'll give you another 5 seconds to think about this for yourself. I know this math notation looks a little bit ugly, but this is the same as this three-pronged symbol here. And then omega is the way to spell out the omega symbol, and then theta is the way to spell out the theta symbol. All right, type it in. Oh, this should be G, sorry. Can I repeat the question? Basically, I'm asking, is F in omega of G? In other words, I'm asking, is G in omega of F, which you should know the answer to already. And then lastly, we're asking, is F in theta of G? All right. So we have some people saying yes and yes. We have some people saying yes and no. All right. So the idea here is, let's go ahead and answer the first one. The first one here is saying, is G in O of F? And we just said in the previous slide, yes, right? We said in the previous slide that G is in O of F because we know that F is already bigger than G for all values as n approaches infinity. If that's the case, then G is in O of F, which means that if this G is in O of F means the same thing as F is in omega of G, then the answer here should be yes as well, right? This is just like playing around with definitions. There's no new computations or new things you have to understand. Why do you have a backslash? Because for most math languages, so there's a syntax that allows you to type math, and the backslash just allows you, if you were to use an actual math programming language, you would use LaTeX, for example, you would get this symbol if you did that. Right, so the backslash is just notation. You can just treat this backslash I in as the same as the symbol that I have rendered properly on the slide. Now, what we said earlier was that F in theta of G is the same as saying F in O of G and F in omega of G. Well, we just proved that F is in omega of G, and we said earlier that F is in O of G, right? Which means that if both of these are true, then this is true too. The answer here is yes. All right. Essentially, what I'm saying for this first one is the G function always going to be underneath F? That's the first question that we're asking. The second question we're asking, is F in theta of G, is saying not only can G be underneath F, G can also successfully be on top of F if you pick the right constant, right? So we can say that for some line, which we proved before, we can multiply this n plus 2 with a number, in this case 3, such that it will always be bigger than the F that we have here. All right. So again, this is just something that you need to like practice and get good at. I don't have a good answer apart from just seeing enough examples until you get it and kind of thinking for yourself and asking lots of questions. I can't explain it more clearly unless you ask me more questions. So G is underneath the first line. Okay, so if G is underneath the first line, then it's in F. It depends on what you mean by in F, right? I can't just say G in F. I have to say either G in O of F, G in omega of F, or G in theta of F, right? So, for example, if this blue line is G and it's underneath the red line, we can, for example, say that F is in omega of G, because G is underneath F. We can also say that G is in O of F, which means the same thing. All right. And we can also say that F, wait, can we say that? Let me think about that carefully. No, these are the two things we are guaranteed to say in this case. Could you say that any two linear functions with the same signed slope satisfy these questions? Yes. All right, great questions. We're going to move on for the sake of time. But if you still have questions, again, office hours are available to you. And also, we definitely want you to review these videos and try to play through the exercises again in your head, right? A lot of times you just have to make sure you remember and understand this stuff, the two most basic bottom levels of Bloom's taxonomy. And if you get stuck with any of that, we're happy to help. All right. So let's go ahead and see where we would want to get more practice. If you want to get more practice, Piazza actually has a great link. In this case, There's a pinned post called Time Complexity and Space Complexity Practice Questions. We have a link to a worksheet in the instructor response, which gives you a bunch of different practice problems. All right. I didn't do big, okay, so this is missing. This is missing space complexity. I'll include it before exam 1 to practice that. All right. I wrote this up at like 1 a.m. last night, my time, so it was very, very late. But basically, I wrote a bunch of questions for runtime that you can practice. And if you want to practice all of this, you can. And this is excellent because if you want to see the answer for something, for example, is x in omega of x squared? Yes or no? Type in chat if you have it. Is this true or false? This one here. Okay, most people are saying false. We got a few trues here. This is saying, is x squared underneath x for all x approaches infinity, right? So is this line x squared? This line here, if we drew a graph, x squared would look like this. And we're asking, is it underneath the line x, right? And it's clearly not, right? X squared will grow and grow and grow and be faster than x very quickly. So there's no way that this could be true because this omega, this big omega, signifies that x squared can be guaranteed to be underneath x if we pick the right constant. And if you just highlight here, it says false. Right, so I've written the answers in white text on the white background. And if you want to not spoil yourself, you just go and answer the questions ahead of time. And then once you need the answer, you just highlight them and you get the answer. All right. So you can see that we've answered, I've answered pretty much all of the questions except for this very last one, which is very, very challenging. So I've made it optional. But if you want to practice, here's your way of practicing. All right. It's really, really helpful if you go and answer those questions, especially for the quiz tomorrow and Thursday. Tomorrow for people who have Monday lecture and then Thursday for you all. So we can't go over this right now. We're going to go and move on. Right. I wrote all of these questions and I gave you all the answers. If you have any questions about how to answer some of these, make a Piazza post. You can see that we've answered nearly every single question and the average response time has stayed fairly low. This is a lie. Sometimes it'll take hours or maybe a day to answer your question. But for the most part, this is the fastest way to get an answer. And, be honest, like, you never expected a professor to answer you anyways. This is a lecture. We're doing our best to answer everyone's question, and we really want you all to learn. So please do ask questions. We will definitely try our best to answer them as quickly as we can, right? Obviously, there are some times where we can't answer them as fast. For example, if I'm writing homework or if I'm teaching, I can't answer during the time. But we definitely have a bunch of people who are trying to keep track of all the questions and do your best to answer here. All right, so let's go ahead and look at some other exercises we're allowed to answer, or we should work on now. Someone asked, hey, how does this actually apply to runtime, right? Like, how does it apply to functions in code? Well, we know that we can figure out the number of steps this function will take, and then we will have a corresponding big O notation to describe it. I'm going to give you all about 20 seconds to try to answer this based on the code that we've seen here. Now, this should be a review from last week because we already saw two-sum slow and did the analysis for it, so we're not going to do it again. But we're going to try to answer these questions. Which of the following are true? You can pick all that apply, right? So let me go ahead and just make that clear. Pick all that apply. All right, 20 seconds starting now. All right, what do we think? Okay, some people are saying A, some people are saying A and B, some people are saying A, B, and C. Some people are saying just B. Interesting. Okay, so first off, the expectation is that everyone should think that A is correct. Everyone should at least all pick A. All right, because what we have here is a for loop inside of a for loop. The inner for loop will run on average n over 2 times. The outer for loop will run on average n times. So if there's n over 2 times being run and the outside is being run n times, then it's n times n over 2. Everything on the inside here is constant time. So then we have, n times n over 2 times a constant amount of work, n times n over 2, right? Outside times the inside, because these are nested, times the amount of work that's going on in the inside, which overall gives us n squared. All right. So that's cool. But then the tricky business that I wanted to bring up during this lecture is that this is also correct, and this is also correct. All of these are correct. Weird, huh? Now, if you have a hard time understanding where I got this from, what you need to do is to go back onto that Piazza post I showed you. And I should link this on the course website, but on the Piazza post, we have a link to the course website, which shows you how to-sum works on a very deep level. All right. I'll send this in chat so that you can have it and read it later. But I literally break down in a lot of detail how this code should work. All right, because I need you all to be able to understand this analysis, and it gives you a good example of how the runtime works. But okay, why does this actually hold true? If you remember, the definition of big O is saying that f is in O of G, right? F is in O of G when we can say some f of n is less than or equal to k times g of n for some constant k as n approaches infinity. All right. Now, if we just use the mathematical definition that we've put here, B and C both satisfy that. N to the fourth will always be bigger than n squared as you draw the graph and you plot it out, right? So if we plot out the graph here, what we see for n squared looks something like this. It's going to grow and it's going to kind of hockey stick. N to the fourth is going to be a sharper hockey stick. And then 2 to the n is like the sharpest hockey stick, right? So if this is n to the fourth, pardon my drawings. You paid tuition for this. I apologize for the quality of my drawings. I saw a meme on Zoom memes for quarantines the other day, and it was like text that was worse than mine, like drawing on the slides, and it was just so sad, right? But you can see, roughly speaking, that as n increases, n squared will be on the bottom compared to n to the fourth and 2 to the n. All right, and that means that this will hold true if g is n to the fourth or g is 2 to the n, right? What I want to say is that based on this graph, I know that n squared is in O of n to the fourth. N to the fourth, n squared is also in O of n 2 to the n. All right. Now here's the clincher. I know that some of you are still probably confused about what's going on, but let me give you this hypothetical, right? Andrew is 5'10". Andrew is no taller than 5'10". Andrew is no taller than 6'10". Andrew is no taller than 7'10". Or actually, let's make this ridiculous. 10 feet even. All right. Assume number one is true. I am 5'10", right? 5 feet 10 inches, which is like 106. I don't know what that is in metric. I apologize. I am not cultured. But assume the first one is true. Is the second one true? Yes or no? Yeah, right. Like if I'm 5'10", then I'm no taller than 5'10", right? If I'm 5'10", am I also no taller than 6'10"? Type 6 in chat if you agree. Cool. And if I'm 5'10", then I'm definitely no taller than 10, right? Type 10 if you agree. And that's what we have here. We know that 2-sum slow actually is running an n squared number of steps as we increase the size of the input. As we increase array here, which is the length of the array is what we define n as, and I should say that. N is equal to array.length here. Always define what n is. You'll lose points on the exam if you don't define what n is. But we know that n is going to be the array length. That means the number of steps will be roughly n squared, O of n squared. And that's going to be a tight bound. That's like the best we can do to describe the behavior here using big O notation. Now, at the same time, we have these other statements that are also true, right? All of these are true. But the second two are kind of uselessly true, right? Like they're true, but they don't give us as good of information as the first one. All right. Yeah, I should be playing basketball and hanging out with Yao Ming if I were 6'10". Yes. If I were 10 foot even, I would need a bigger apartment. But basically, the idea here is to show that big O can be used to demonstrate slightly useless information, right? Saying that the sky right now is not purple does not tell me whether or not the sky is blue, and it does not tell me that the sky could be purple later today. But it is true, just like how it is true that I'm no taller than 10 foot even, right? Okay. So hopefully that gives you some intuition for how this stuff works and how it relates to runtime. We're going to look at another couple of examples. We're saying in the worst case, which of the following is true? I'll give you 20 seconds. Remember, big omega is the same as saying, right, F in omega of G is the same as G in O of F. All right. So 20 seconds, work on this now. Also, for those of you who are in chat making basketball memes, that last one was too soon. My heart. You should feel bad for making that joke, bud. All right. Which of these are true? Select all that apply. All right. A lot of people are punching in A, and that's correct. A is definitely true. Right. This is saying that in the worst case, if we translated A, it's saying that in the worst case, 2-sum slow will take no less than n squared steps, as in where n is equal to array.length. All right. But we can't say that 2-sum slow is in omega of n to the fourth, because if we remember, neither of these are true. These are all incorrect. So let's put an x on B and an x on C. What does the spotlight feature do? What happens if does this do anything? Oh, yeah, we're not going to use that. Okay, so if we draw this out on a graph, what I'm saying here, remember, is that we had these 3 different lines from before. Right, and I'm saying that n squared is this line, and this is representing the number of steps we know that this will take in the worst case. Well, we're asking for B, will the number of steps be no less than n to the fourth in the worst case? That's what we're asking, right? But we know that it's already going to be n squared, which is less than n to the fourth as n approaches infinity. So there's no way that that could be true. And the same argument can be made for 2. to the n. Right? If you're a little bit shaky about this, ask during the break, ask during office hours. We're going to move on. One last one here. Oops, that's not right. All right, so I said in the worst case here. Now I'm saying in the best case, which of the following are true? All right. Notice here that I went and defined worst case and best case when using big O and big omega. Omega does not just mean the best case. It can be used in the worst case as well. You can use it because it's just a mathematical notation that shows you stuff, that shows relationships between mathematical functions. Go ahead, take 20 seconds here while I go and rage against the injustices of the world by typing this. All right, what do you think? Which of these are true? Select all that apply. All right, so if you understood the previous slide, then you should understand this slide. Most people are saying none, which is correct. We know that the best case here, we know that the best case is 2 sum slow is in O of 1 in the best case, where n is equal to array that length, right? We know this from last lecture. If that's true, that means that there's no way that the minimum number of steps that 2 sum slow takes in the best case is at least n squared, right? That at least is the important part. Let me say that again. This is saying for A, 2 sum slow in the best case takes at least n squared steps in the best case. But we know that's not true because we know that it can't take more than a constant amount of steps, right? If we know that it can't take more than a constant amount of steps, then there's no way it could take at least n squared steps, right? Now, I wrote this on top here because frankly, this is like one of the most common things people get wrong when learning this stuff. There's so many people who get this wrong that there are some online resources that get this wrong. And it's a problem, and none of my students should ever fall into this trap. So I'm going to shout it from the rooftops that omega does not mean best case. You can use omega to talk about best case, but we can also use omega, like in the previous slide, to talk about the worst case, right? We talked about omega in the worst case. We can also talk omega in the best case. We can also talk about omega in the average case. It's like totally legit to do that. Theta does not mean average case. Big O does not mean worst case. Oops, I said best case instead of worst case. And you need to like drill that into your head one way or another, all right? It's really important to me that you know this, so I'm going to be repeating it a bunch and testing you on the quiz. All right, so now we're going to take a break. If you had questions about any of the stuff from before, feel free to ask, but at 3:30, we will go ahead and go back and start looking at stuff again. Someone's asking in chat, omega is lower bound, big O is upper bound, and theta is both. Yes, that's exactly correct. Omega is considered to be the lower bound. Big O is not the worst case. Big O does not semantically mean the worst case. Big O is just some mathematical notation. You can use it to describe the worst case. You can also use it to describe the best case. We did that last week. So you can use big O, big theta, and big omega in any of these cases, and you don't necessarily need to associate, you shouldn't associate any of the mathematical notation, so big O, big theta, big omega, with any of the coding cases, conditions. So don't try to think, oh, big O always is used to mean worst case. That's not true. All right. I wish my cat were able to sleep under blankets. He does, but he doesn't do it on his own. I saw a video the other day, like yesterday, about how a cat just kind of nudged a human under a blanket until the human let the cat in, and then the cat cuddled up, and it was adorable. Any questions about runtime? Either that, or we can talk about Piazza announcements.
Yeah, I had a. Oh, go ahead, man.
Oh, my bad. So I have a question about recursion. if we have a function that calls another function and then that function calls it back, the function that called it, is that considered a recursion or?
Yes, that's a good question. So let's go ahead and I'll answer that question first, and then I think someone else had a question too, Kevin, I believe. So let's say we had a function A. Function A calls function B. Function B calls function B and has a base case. All right, so we know that function B is recursive. Function A is not recursive. Function A just happens to call function B. It might not know that B is recursive. There's no way A would know that B is recursive because A doesn't have access to the body of B. B itself, since it actually does call, is recursive. All right. But when we're on homework, it's okay to define A as your recursive function. All right. On quizzes and tests, we wouldn't consider this case to be recursive. All right, so this is a little bit confusing, but what I'm saying is that you can have a recursive helper function and use that to solve, for example, the questions on homework 1. But on quizzes and tests, we're not including that as like the case when we're saying A is recursive or not. All right, does that answer your question, Anwar?
Yeah. Okay. Okay. Another example. What if B calls A back again, and
If
then
B calls A and then A calls B, that's called mutual recursion. We don't cover it in the class, but that would be recursive.
okay, perfect. Thank
Great
you.
question. That was excellent. I'm going to use this video. We're going to post this video, and just because you asked that question, it's so good. What case would we use theta? We use theta because when we want a type bound, when we know that this runtime, this function very directly, very closely resembles the runtime of the function. All right, we'll take a look about this later on, and you can also check out the practice. Okay, Kevin, did you have a question?
Yeah. So I know you were saying for omega, that just means that the function it can't take any less steps than that, correct?
Yes.
And then so for big O, is it can't take any more steps than that? Is that how it is?
Yeah. Big
Okay.
O is basically exactly as you described. We say that G is an upper bound of F, which means F grows no faster than G, but it also means what you just said in the context of runtime, that you can say that the number of steps that this Java function takes will never exceed whatever mathematical function we put in the big O.
Okay, that makes sense. And what is it in terms of theta?
Theta is just both upper and lower bound.
So
Theta
it's just
means
within?
yeah, it's within.
Okay.
Yeah, we'll look at some. I think it's hard to like review this and really get it under your fingers the first time around. So I really appreciate you asking the questions. But basically, F grows no faster and no slower than G, right? That means that the number of steps is modeled very, very accurately by the current function that we have inside of the theta.
Okay, that makes sense. And yeah, like you were saying before, that's why, because like you're saying, there's some online sources that even say that. I saw that before where they're saying like omega is always like worst case and O is always best case and things like that. So that's what I had thought before.
Yeah, we're gonna fix those habits in this class. You'll learn
Okay.
fast or you'll lose a lot of points on the quiz. That's basically how I'm going to have you all learn it. But I also will repeat it like 1,000 times. So hopefully one of those 1,000 times will stick.
Okay, cool.
Nice, great questions. All right, we're gonna keep going.
Hello.
Yeah, what's up?
I just wanted to ask really quick. So you said we're gonna get an email that like is a survey.
Yeah, I see from the post on Piazza and from comments that it's not working. So you should go. I'll go and double check that after this lecture. Okay.
Okay. Yeah, I got an email, but all it says is here's the list, and it doesn't have anything else.
Yeah, I understand. I will go and check up with the people who send out the surveys.
Okay.
It looks like another one was sent that looks good according to chat. So you maybe just have to refresh your inbox. Okay, so for those of you who don't know what's going on, please read the latest announcements. I'll go over them during the next break if no one has questions, but these announcements are super important. Let's go on. Okay, so type sorting in chat if we're here and we're ready to learn again. we're going to start talking about sorting. How long does the survey take? I'm not sure. Probably no more than 30 minutes. Looks like it took most people 10 minutes, or at least took one person in chat 10 minutes. All right. We're going to talk about sorting. I'm going to go a little bit fast. Everyone's seen sorting before, hopefully. Even if you haven't seen sorting in coding, you've like seen sorting in real life. For example, like sorting books, or like sorting your room, or sorting your kitchen, right? Sorting happens in real life, so you can rely on some sort of intuition when reasoning about them in algorithms. If nothing else, you had to like put numbers in order when you were in like primary school, right? In elementary school, that was something that we all had to learn in math class. And another thing to notice is that sorting relies on arrays and lists and numbers, which are relatively like straightforward. Everyone knows those, right? Good training ground. That makes it a good training ground before we hit more challenging algorithms. Essentially, we have this idea of all these questions we want to ask about algorithms. Why don't we ask them about sorting algorithms, which we all feel somewhat intuitive toward and have some sort of like background in, before we go and look at more challenging problems. They basically analyze, evaluate, and create on a problem you're familiar with, right? Analyze, evaluate, and create are levels of Bloom's taxonomy, which are the more challenging levels. So we want you to practice harder skills on easier algorithms and easier problems, so that once we get to the harder algorithms, your skills will already be up to stuff, right? Sorting algorithms illustrate important techniques that can be applied to other domains. We're going to see divide and conquer, for example, and we're also going to see the use of data structures. So sorting is kind of like our first algorithms kit, basically our first foray into the land of algorithms. We're going to pick some really easy algorithms to start with that everyone should have seen at least before, and it will feel a lot like review. But we will be answering some of the more deep questions, and I will still write problems that you will get wrong, so don't let your guard down, right? I will be asking questions that are deeper since you already know this topic and you've probably seen it in the past before. So it's on the exam, so no matter what, you're going to have to learn this, all right? And it's useful in interviews, which is 100% true. All right, so let's just define the sorting problem real quick. It's defined as following. We start with a list of integers in some order. The output is going to be a list of integers such that each element of the original list exists in the new list, and the elements are arranged in non-decreasing order. Non-decreasing order just means that if you have numbers that are repeating, for example, oh, that's a terrible color for this background. Let's use this. If you have 1, 2, 2, 3, 4, 5, this is a non-decreasing order, right? Because 2 and 2 are the same value, so they can't be increasing, but they're also not decreasing, so they're non-decreasing, right? That's just all that means, right? For numbers with the same value, you're non-decreasing. All right, so other things we need to know? Nope. Okay, cool. Right, so not scary. This is just your obvious definition of sorting. Just remember it. We're not going to like harp on this too much. What is important, what you do need to write down and pay attention to, is this slide. Basically, there's a couple of different questions we ask when we're talking about sorting. We asked about the best case, the worst case, and the average case, just like we did last lecture. And we also ask, is this algorithm in place? Can we only use a constant space in order to solve this problem, in order to sort this list? And when I say constant space, I mean that the original array isn't counted toward the space we use. We don't make any new lists or arrays when we are dealing with the algorithm. That's what it means for it to be in place. So let me go ahead and write this again. Constant space in this case means we don't use any new arrays or lists or other data structures to do the sorting. That's what it means to be in place, right? You can define variables that hold numbers. You can use variables that take constant space, but you cannot create new data structures that will be heavy, right? It can't be like in elements in a new array. That would be not constant space and therefore not in place. Lastly, this is the definition that is the most foreign. Who has heard of stable sorts before? Type in chat stable sort if you've heard it before. Type in chat question mark if you didn't. Okay, mostly getting question marks here. All right, no one's heard of stability before. Stability is something that I wish they taught in 2720, but it sounds like most people haven't heard about it before. Here's the trick with stability. If you have two numbers of the same value, but they have different colors in this case. Hopefully no one has difficulty seeing these colors, but let me know if you do. That we have a red 5 and a blue 5. They're different shades of 5s here, right? If it was red 5 first and then blue 5 before we sorted the list, and then after we sort the list, it's still red 5 first and then blue 5, then we call it stable. If it's not stable, that means the red 5 and the blue 5 can be arranged in a different relative order after it sorts. Right? So stability means will elements of the same value stay ordered relative to each other? And the only way you can really figure this out is by having a separate property that you also are keeping track of the order. Right? So in this case, the color of the numbers as well as the values of the numbers itself. You might think about how that might be relevant in real life. We'll talk about it in about like next week. But stability in sorting is really important because, for example, if you want to sort everything by last name, let's say I had a roster of students, I sorted everything by last name, and then I also wanted to sort everything by first name so that everything would be sorted by last name first, but then if there were any tiebreakers, we would sort by first name. Then we would want a stable sort to sort twice, once for the last name and then once for the first name. We could also use a comparator sort to do both at once, but stability gives us some advantages that we'll talk about later. All right. So we'll talk about stability in these examples that we'll look at next. So let's just go ahead and review some sorts that we've maybe probably seen before. Type selection in chat if you've seen selection sort before, type question mark if you haven't. Okay, a lot of people have seen selection sort, right? The intuition behind selection sort is we basically pick the smallest element, then we pick the next smallest element, then we pick the next smallest element after that. And every time we pick the next smallest element, we're just creating a list, a resulting list that has all of those things in order, right? So if I pick the smallest element out of a list, then I will put it in my new list, then I'll pick the second smallest and put it in my new list, and I'll just keep doing that until we pick everything from the original list and put it in a new list in order. Did someone have a question? I can't tell if someone spoke up in the mic. Okay, then let's go ahead and look at this example. Go ahead and type questions in chat if you have questions. If we have this original list that we saw from the previous slide, what's the smallest element in this list right now? Type it in chat. What's the smallest number in this? 1, right? Cool. I don't know why someone typed A, but hopefully you meant 1. Okay, so we pick 1. We're gonna put 1, take it from the old list, put it in the new list. So on the right-hand side, I've made a new list. It has 1 in it and nothing else, right? Now, we're going to go ahead and do that again. Next thing we pick is the next smallest element. We already used 1, so the next value is what? Type it in chat. 2, right? So we pick 2 and then put 2 in the new list. You can see that we're putting it to the right of the 1 so that it stays in relative order. We keep doing this. We're going to pick 4 next. Now, here's the part that's tricky. Which 5 do we end up picking here? What do you think? Red 5 or blue 5? Take 10 seconds. Okay, or just type it in chat. Red 5. Everyone's already said red 5. All right, and this is only true. We pick red here only because we go from left to right. Right? So in other words, we need some algorithm when we're doing the min, algorithm min. Let's say the input and the output is defined here. And I'm not going to define the input and the output because I don't want to spend forever on this, but let's just say, min is equal to negative infinity. Then we say for I is equal to 0, 1, 2, ... n minus 1. Then if min is less than, if the current element of the array, so we know that the input is going to take in at least some integer array ARR. So if array at I is less than the current min, then min is equal to array.I and then return min at the end. This is literally the min we would have to use in order for us to pick the red 5. All right. I'll give you 10 seconds. What happens if I went and said that this is less than or equal to instead? 10 seconds starting now. What 5 would I pick if I added this equal sign? It grabbed the second 5. It would grab the last 5 in the list if we added the equal sign here. Right? So because we have this less instead of equal, That's the kind of key here, right? And if you, those of you who are on the video right now, who's watching the video, rewind that. Like really, make sure you understand the nuance of adding an equal sign here. This is that level of complexity I'll ask you on the quiz, and on the test, right? Oh, that's a really good question. This is gonna be fun. Yeah, but I said it in lecture, so now it's fair game, right? So we have this code, which means we'll pick the red 5. Red 5 gets picked, then we pick the blue 5, then we pick the 9, and then we're done, right? So I'll give you 20 seconds based on what we have here. Is this a stable sort, and is this in place? Give you 20 seconds to try to answer both questions. Don't type it in chat yet. And then afterwards, we'll type it all in all at once, all right? So I'm gonna ask, why do we choose the blue 5 first if we have an equal sign? Well, that means if we had an equal sign, every time we saw an element that's the same value as the current min, then we would replace the min with the current value, right? So if we saw a blue 5, min will eventually become the red 5. And then if we had an equal sign here, then we would compare the blue 5 against the red 5, realize that they're equal, and then replace the red 5 with the blue 5. How do you know which 5 is being picked without seeing the colors? This is why we're using an example in the slides instead of on code, right? It's easier to demonstrate this in the slides. It would take a lot of setup in code, but you would just trust that that's the case. You would just know in some sense, all right? Which is why we use pictures instead of trying to show you in code. All right, go ahead and type in chat. Is it stable? Is it in place? Okay, we got some people saying that it's stable. Most people are saying it's stable. Some people are saying it's in place. Some people are saying it's not in place. Well, let me ask you this, right? Type in whether or not we make a new array. Type new array if we made a new array here, if we made a new list. Type new array if we did it. Okay, we made a new array, right? We started with an empty list and we started shoving elements into it as we took on steps. And if we did that, then that means it can't be in place because we made a brand new array here, right? So if we made a brand new array and it's as big as the old array, that means that we use not constant space, we use linear space, we used O of n space. But this is indeed stable based on what we talked about here, right? So it's not in place, but it is stable. All right, the next thing that you would want to know, right? Really, we're just practicing figuring out what stable and in place means, right? On algorithms that you should have seen in the past. Is if we have selection sort like this, then how do we, okay, someone's asking what is in place again? We'll look at it in a second. We're going to look at a example for selection sort in place. So let me try to answer this and talk about this. And if you still have questions after this slide, you can ask me, all right? So how do we do selection sort in place? We said that in the past, this is not in place because we made a new array, right? So making a new array makes this a problem. In order to have it in place, we have to use constant space, which means that we're just rearranging the original array. We have to modify the original list, not make a new one. That's what it means to be in place. Not only do we have to modify the original list, we can't use any new data structures while we're doing that, right? So in order to make this an in-place algorithm, we have to use swap to put the next smallest element in the appropriate spot in the list, all right? I will give you 5 seconds to let this sink in, and we'll just take a look at the stuff that we had, the exact same list we had before. All right. So what we're going to do is we're going to give every one of these numbers an index, right? We know that 9 is index 0, 4 is index 1, red 5 is index 2, 1 is index 3, blue 5 is index 4, and then this 2 is index 5. The first thing we have to do is figure out what goes in index 0. What number should we put in index 0? Well, it's number 1, right? So we would have to swap index 0 and index 3 like this. We swap 0 and 3, so 1 is where the 9 used to be, and 9 is where the 1 used to be. With me so far? We haven't made a new array, we just changed the ordering of the existing array by one move. If we keep going, I'll give you 10 seconds. What's the next swap that we have? What's the next call to swap that we would have? What next elements do we try to modify, and which elements do we pick to modify them? Swap 1 and 5. Yeah, the question is, what is the next step here? That's really what I'm asking. Someone also asked, each iteration goes through the entire list. Yeah, we'll see that to be true soon. All right. So we swap 1 and 5, which means that the 2, which is the next smallest element, goes where the 4 is, and the 4 is stuck at the end here, right? Cool. So hopefully this isn't too scary. We'll keep going. We'll do the 4 next, right? 4 gets swapped with the red 5 because 4 is the next smallest element, right? Someone mentioned before we have to look through the entire array to figure out what's the next smallest element, so we do so here. And then we do, the interesting part is we'll go and find the blue 5 and swap it with a 9. All right? This implies a certain amount of code written in a certain way. But we're going from left to right, and we're just saying if it's less than, if the minimum number we found so far is less than the current number we're at. Sorry, let me try that again. If the current number we're at is less than the number we found so far, then do the swap. Otherwise, don't do the swap. All right. So in other words, this is only true because we go from left to right and use less than. Right? If we use less than here, and instead of less than equals, in this case, using less than will cause the 5, the blue 5, to be picked up first, and then we'll never pick the red 5. Because remember, we shifted the red 5 all the way to the right, which means that we'll see the blue 5 first, and we're only saying if the next thing we see, the next element, this red 5, was less than the current smallest element, which is the blue 5. Only then would we set that to our minimum and do the swap here. Okay. Once we see the code, this will make more sense, but I'll keep this here for the sake of clarity. Then we go and swap the last 5 here, and then we're done. So, question, based on what we have here, based on the example we went through, is this stable? Is this in place? Take 10 seconds, answer it for yourself. Y'all, every time I ask a question, I'm going to ask for 10 seconds. Try not to give it away if you can, right? All right, go ahead. It is in place, but it is not stable. Yes to in place, no to stable. Because if you look at the original list, it was red 5 first and then blue 5. But the result at the end was blue 5 first and then red 5. And that's the kicker, right? Stability means that you are keeping track of numbers of the same value and deciding if their relative orders are preserved in the new sorted order. In this case, red 5 went first and then blue 5 went next in the original list. But we don't have that in the resulting sorted list. Red 5 goes second in this list, which is why it's not stable. All right, there are some other nuances here. We could come up with other examples here that describe why this isn't stable. It's not just because we use less than here, but there are some other counterexamples. And it's not easy to make this in-place algorithm stable. But for now, just know that this was not stable, but it was in place. All right, let's just go ahead and take a look at the code now. I'll give you about 10 seconds. Wait, let's go through and talk about what the code does, and then we'll go and look at the actual algorithm. Yeah, I want to do this. I want to do this now. Visual Algo is a website that we use sometimes to visualize algorithms. That's why it's called Visual Algo. It's really cool because it has all of these different sorts, and I'm going to show you selection sort. So we created an array here. We're just going to go ahead and sort it. And when we do selection sort in place, what we're doing is we're going through, and the blue here shows how we're trying to find the minimum element. Sorry, the green here shows the minimum element. Let me try that again. Right, we start with this element. We're trying to figure out what should go in its place. We're going to want to put the 2 where the 3 is right now eventually. And we're going through and looking at each element and trying to find the smallest element so far. Right? What's smaller than 3? Right now, nothing's smaller than 3, so we haven't picked anything. But then we found that 2 is smaller than 3, and now it's the red one, right? That's the smallest element we've had so far. And then we keep going. There are no other smallest elements. So we swap the current element that we're at against the 2, right? And then we keep going. We go and we find the next smallest element, right? 44 is not a very small element, so 5 will beat it. 3 will beat 5. 4 will not beat 3, so 3 is the next element we have to swap. 38 immediately gets replaced by 5. Nothing else is smaller than 5, except for this 4, which is now the new thing that we want to swap, and so on. We're going to speed this up a little bit, because you're going through and you're seeing the next element that's the smallest. We're just keeping track of the min as we go through from left to right. And then when we find a min, then we swap it with the existing elements, right? The next element that's not orange gets swapped here. Cool. Now we're going to see what that means in code. You can see that they even show you the pseudocode and walks it through step by step. I'll share with you the link so you can play around with it in your own time. I find this website really, really helpful. We're going to take a look at the pseudocode as it's written for this class, which is essentially the same thing. We go through from left to right, and we're going to say that each time we do that, we have a min index, right? Min index is the current index we're at, and that's just the smallest number that we have so far, right? If we look at this example, we started with 3 being the smallest, and then at some point, we're iterating through in the inner for loop, right? From I plus 1 all the way to n minus 1. And saying that if the current element is smaller than the min element, the index of the min element, sorry, the element as determined by the min index, then we'll replace the min index with the current index itself, right? So we have an I that we're going through, but then we have this J. This J just means the green here. The green element is what J is at currently, right? So in this case, 0, 1, 2, 3, 4, 5, 6, 7. J is at index 7. And it's saying that list of J would be 26. And it's comparing it against list of min index, which in this case would be 0, which is 3, right? So that's what this bit in the middle is doing. And we go through and we literally go through the entire rest of the list. We have to, because there might be a min element that we miss if we don't go through the entire list. And once we do that, then we go to the next part of the code, which says temp is equal to list of I. In other words, we do the swap. And since code is more hard to do the swap, it's harder to do the swap in code than it is to do in the graphic. We have to write 3 lines to do the swap. We have to say temp is equal to list of I. So give me the element that I'm currently at, save it, then make that element equal to the smallest number that I found in the rest of the list. And then eventually, the previous place that element lived is where temp is right now. Okay? I'm going to give you all 2 minutes to try to find the best case, the worst case, and the average case here, and how much space it uses. You got 2 minutes starting now. I'll open up the poll. My cat really wants something. Can anyone else hear the cat meow from my mic? Okay, so this video is just gonna have my cat meow at random intervals. Great. It's not even time to feed him. It's kind of like another 30 minutes until it's next time. Maybe he just wants attention. It's hard during the middle of the day because both my girlfriend and I are at work, right? You've got a minute and a half. Try to look at this code, try to understand it for yourself, and then try to figure out what is the best input we could give it that takes the least number of steps. What is the worst input that you could give it that takes the most number of steps? What's going to happen on average? And how much space do you think is being used? Okay, you got 1 minute left. And again, I'll always say this because it's always true. You will just try your best on these. Anything that's class participation related is never graded on correctness. I only care that you're trying and thinking so that you can exercise your brain and get better at this problem solving stuff. So even if you get it wrong, that's 100% okay. I use this stuff in aggregate. If a bunch of people are giving me the wrong answer, that means I didn't do a good enough job explaining, and I should take more time explaining this so that everyone gets the correct information, right? If everyone mostly gets it, then I know I can move on and we don't waste time making most of you feel bored. Right? So this is why we need everyone to participate. There's about 13 of you who still haven't answered. We got 20 seconds left, so go ahead and start putting answers now. Give it your best shot. Remember, you have to answer all 4 questions, so if you can't see how to submit it, maybe there's more questions if you scroll down. All right, still about 8 of you left. 10 seconds left. Go ahead and punch in your answer, whatever you have. Come on, can we get to 50? One more person needs to vote in order to get to 50. All right, we're gonna move on then. 49, very good. Okay, most of you thought that the best case runtime is O of n. Most of you thought that the worst case runtime was n squared, as was the average case runtime. And there was a split between how much space is being used, either O of 1 or O of n. Now, if we just go through and look at all of this, the best case, the worst case, and the average case are all the same. The best case, the worst case, and the average case. First, we have to define what n is, right? Go ahead and type what n is. What is n in this case? N is defined as what? Length of the array, right? Array.length, just so that we have it. And it's also said here, just size n, so n is n. But if that's the case, then O of n squared is the best case, the worst case, and the average case in this situation. Let me explain why. It doesn't matter what sort of array you put in, because no matter what, when we have this for loop, the inner for loop will always run, right? The outer for loop will run roughly n times. What if the array was already sorted? Let's go ahead and play this out. What if the array was already sorted? If we create a sorted array, this is why I love this freaking app, right? Like, it's already sorted, and we sort using selection sort, we still have to look through every single element to try to find the minimum, right? So that means we'll iterate through n times each iteration for the next element, and then there's n such elements, right? Each of these orange columns required us to go through and look through the rest of the array at least once in order to get it. So we know that the outer for loop takes n. Outer for loop is roughly n iterations. Inner for loop is on average n over 2 iterations. Overall number of iterations is n squared over 2, which is the same as O of n squared. Everything else in this code is constant time. So, setting the min index is obviously a constant time operation. Setting the min index up here was constant time. These checks are all constant time. This swap here, these 3 lines are constant time. So given that, the only thing that we need to count for is the number of iterations that all of this happens at. If the outer for loop takes n iterations and the inner for loop takes n over 2 iterations, then you multiply these two together in order to get n squared over 2, which is O of n squared. You could get a better best time complexity if you hard coded in checking for the sorted case. But we don't have that here. Why is the inner n over 2? I can't explain that right now, but basically you should go and look at the runtime analysis from here. And there are, I think, previous lectures that talk about this in more detail. If you look at the video for the lecture that we covered, the first runtime, we talked about print pairs, which I think should help. Yeah, someone in chat is giving you a little bit of advice, and that is a good point, that each iteration decreases how much of the array is compared by 1. So at the beginning, you'll have like n, and then n minus 1, and then at the end, you'll be like 1 and 2 and 3, right? So on average, you'll be like somewhere in the middle. Okay, so space complexity, let's just go over that real quick. Space complexity here is O of 1. Because we said that this was going to be an in-place algorithm, right? All we did in order to define the space here, we defined an index I, which is constant space. We defined a min index. There's only one of them at any point in time, which is constant space. We defined a j, which is constant space. None of these swaps or reassignments count as extra space. They're all just modifying an existing array that came in as input. So let me go ahead and type that in big red letters so that you all don't forget. When computing space complexity, the input does not count toward the space used. In fact, this is such a big deal. Everyone type this in chat right now. in big caps, so I know that you've already at least internalized this once. When computing space complexity, the input does not count toward the space used. Type that in, hit enter, and then we'll move on. In big text, yes, please. This is one of those other things that people get wrong all the time. So I'm trying to make it a big deal so that you don't miss it on the quiz. And so it's a little bit silly. You remember the time in lecture where your crazy professor made you type this like dumb sentence into chat. And you'll remember it. That's the key. You'll remember it, which is what's important. All right, so moving on. The next thing we'll cover is insertion sort. All right. So essentially for insertion sort, we're going to talk about another version of n-squared sorting, which actually turns out to be more useful than selection sort. Selection sort is kind of terrible, but it's more intuitive. But in selection sort, we want to essentially, sorry, for insertion sort, we want to essentially sort the same way we would be sorting a deck of cards. Let's say we were playing a card game like poker or Big Two or some other card game, Hearts, and you were being dealt cards one at a time. What you would do is start with an empty hand, pick the first card up and put it in your hand. Then you would pick the second card up and decide whether or not it goes to the left of the first card or to the right of the first card. You would pick the third card up, figure out if it goes at the beginning, in the middle, or at the end. You pick the fourth card up, do the same thing. And then as you are inserting into the list, the amount of cards you have to consider gets bigger and bigger, but you're maintaining a sorted list in your hand, a sorted set of cards in your hand as you go through. I don't know why someone copied question 4 from the homework into chat. Do I have to I'm so confused. Anyways, let's just look at this example. All right. We have this original list that we are going to continue to use. And in this case, we're going to try to figure out what the smallest number is. No, sorry. We're going to pick the 9. We're going to pick the 9 and put it in the new list, right? We pick the first element from our original list and just put it in our hand. 9 goes in. Then we're going to pick the 4. Is the 4 going to go before or after the 9 in the new list? Go ahead and type in chat if you have it. Okay, we got some befores in chat. Yeah, cool. And then we pick the 5, the red 5. Red 5 goes before or after the 4, before or after the 9. Where does this go? Just type in chat where you think it goes. Between, in the middle, after the 4, or before the 9, however you want to say it. Yeah, that's true. Now, again, we're going to try to kind of be specific on the results here. We want to say essentially that the 5, or rather, we will always put things before the first element that is larger. That way, you won't get confused when we see the blue 5. All right. So when we pick the 1, that obviously goes before anything. When we pick the the blue 5, we made the rule that we will always put things before the first element that's larger. So if we follow that rule, that means that the blue 5 goes before the 9. All right, that's the trick we're saying here. We made a rule on the left here in red that we will always put things before the first element that is larger. Now, if we keep going, we pick out the last element, which is a 2, and we put that before the 4. All right, is this stable? Is this in place? I'll give you 10 seconds. Don't type it in. Okay, is it stable? Stable. People are saying yes to stable, but not in place. That's true. Yes and no, right? Because we made a new list. You should be catching on to this now. We made a new list. We allocated new space in memory for our computer, and therefore it's not in place. We didn't use constant space, but it is stable here. Okay. Moving on. Let's go ahead and take a look at the in-place algorithm, which is what's like the more interesting or important part. If we want to do this in place, we're going to have to not make a new list. So the intuition here is to maintain an index of the elements we sorted so far. We're going to pick all the next elements from the list, figure out where it goes, and then insert by shifting all the elements all the other elements to the right by 1, and then we increment the index. Now, this is a bunch of words. You may or may not understand what this means, and I'm not going out of my way to try to explain it because I know the example will help you more. So here's the example. All right, we're gonna go and show you the demo first before the pseudocode because I think this will help more. In order to show you the demo, all I have to do is click insertion sort, and now I get a new array. It's so cool, right? So we'll play this. We're gonna play this slow. We pick 3, that's already sorted. Then we're gonna find 44 and figure out where it's supposed to go, before or after the 3. It's after the 3, so we put the 44 right where it is. We figure out where the 38 is supposed to go. It goes before the 44. So we make that swap. 44 goes over by 1. It's not going to go before the 3, which is why 38 gets slotted in the middle there, right? We check 5. Is 5 going to be, this is going too fast for me to narrate. Let's try that again. We pick 5 next. Right? Everything on the orange here is sorted, right? It's sorted just like we saw in the previous example. We have a hand of sorted elements so far. We pick the 5. We figure out, is 5 going to go before the 44? It is. So we're going to shift 44 over by 1. Is 5 going to go before the 38? It is. So we're going to shift it over by 1. Is 5 going to go before the 3? It's not. So we're going to leave that alone and then put 5 in the space that we made by shifting everything over by 1, right? We do this for 44. Do we shift anything? Yes or no, chat? No, right? Because is 47 going to be to the left of 44? No, 44 is smaller than 47. And therefore, we put it, right? We do this comparison, and then we put it exactly where it was. We do this for 15. Is 15 smaller than 47? Yes, shift it over by 1. Is 15 smaller than 44? Shift it over by 1. Is 15 smaller than 38? Yes, shift it over by 1, right? The current element is the one in green. X is the red element. Is 15 smaller than 5? No, so we just let 15 fall into the empty space that we created by shifting everything over by 1. Now I get to actually play this, right? In this case, 36 goes next. We shift it over, all the elements over until we find the right spot for 38. And then we keep going. I'm going to do this faster because we want to be good on time. Right, and you can see that for this, you can already start thinking about what the runtime of this is and what the best case and the worst case should be, right? I want you to start thinking about that question in your brain when you're like looking at this, right? I'll play this one more time, and what I'm asking you is, what do you think the best case arrays are? What do you think the worst case arrays are? What do you think the average case will look like? Don't type it in chat, but start thinking about that. I'll play this one more time while you answer that question. And then we'll go ahead and actually launch the poll while I replay this. There we go. Oops, that's not the right button. There we go, relaunch. All right, you got 2 minutes. So let's see if we can try to figure this out. What do you think is the overall runtime just based on conceptually what's going on here? What do you think the best case should be, and what are the arrays that looks like? And what do you think the worst cases will be? Right, and we'll look at the pseudocode now. This is the same type of pseudocode as we saw in here, but now it's hopefully formatted in a way that you should be familiar with. Can I repeat the question? These are the 4 questions we're asking. What's the best case, the worst case, and the average case, and how much space does it use? Is it? Yeah, okay. It's asking all 4 questions. Excellent. Yeah, you can answer it in the poll. You got about a minute. It's about 20 of you who need to answer. And we have 1 minute, so, start thinking, but, you got about 40 seconds left now. No rush. Okay, there is a little bit of a rush. I lied. All right, about 8 people still need a vote. Shouldn't the question be asking big theta rather than big O? We assume when I'm asking this question and I'm using big O that we're assuming the tightest possible bound, the tightest possible upper bound. That's the assumption we're making, but using big theta would actually be more correct because then you're guaranteed that tight upper and lower bound. That's a great question, though. Thank you for asking it. All right. So I'm going to go ahead and end the poll now. Let's see what you got. The best case here is O of n that you saw, and that's correct. The worst case is O of n squared. The average case is probably O of n squared, and then everyone didn't fall for it this time. Most of you thought that the space being used is O of 1. Now let's go ahead and take a look at why. Now, I want to first start by just identifying the original stuff that I talked about in the code, right? I want you all to be able to take the big idea in white here in this white box and correspond it to the actual code that we write. So when we say we are maintaining an index of the sorted elements so far, if I'm maintaining an index, I mean this index here, right? It's going to be the sorted elements so far. At the beginning, only the first element is sorted, then the second element and the first element is sorted, then the third element, the second element, and the first element will be sorted, and so on, right? And we'll increment the index. From there, we're going to pick the next element that goes in the list, pick the next element from the list that we need to insert somewhere, and we need to figure out where it goes and insert it by shifting all the elements to the right by 1, right? So that's basically all of this code here, right? We use J to denote which element that we're currently shifting, and we say that while J is greater than or equal to 0, and the element at J is greater than the current element we're about to put in, then I have to put the element at J over by 1, and then make J go down by 1, right? So I'm shifting all the other elements to the right by using this code, this while loop here. And then at the end, once the while loop is done, I can just simply put the element that I'm trying to insert into the empty space that J provides, because by the time we're done with this while loop, J will be pointing to the first element that's smaller or equal to next. Okay? I actually think this sort might be stable even though it's in place. Yeah, it's going to be stable because of this here. Okay, neat. Anyways, let's go ahead and take a look at the runtime. If we look at the runtime here, we need to figure out what is the best case, what's the worst case, what's the average case. Well, the best case runtime is going to be when the array. What do you think? Type in chat if you have an idea. What do you think is the best case runtime that would lead to us being able to say that the runtime for the best case is O of n? Okay, basically everyone's saying if the array is already sorted. Best case is when it's already sorted, which gives us O of n. Now let's look at why that's the case in the code. There's a for loop, and then inside is a while loop. If the while loop never runs, then the overall runtime should be O of n because everything else is constant time. And if the while loop only takes a constant amount of space and doesn't iterate all the way through, then we should be good, right? Well, when is that the case, right? Whenever we look at the example here, if we're looking at an already sorted example or a nearly sorted example, that might be better. We're seeing that insertion sort, when we are trying to figure out where it shifts, the more sorted that it is, the less likely it has to do any sort of sorting, any sort of shifting on its way over, right? 9 doesn't have to go anywhere. It's already in the right place. This other 9 doesn't have to go anywhere. So the while loop's not firing when we're looking at this. The inner while loop here is not firing. It's only if we happen to have an element that is slightly smaller than the last elements, right, that we actually have to fire the while loop. So the perfect world is if everything is already sorted, because then the inner while loop will never fire. we never have to do any sort of extra work to shift everything over by 1, which is what the while loop takes charge of. And we end up not having to deal with the while loop at all, which is the overall runtime, leads to the overall runtime being O of n. Now, the worst case here will be when we have, well, the opposite of this, right? If this works well when it's already sorted, you can kind of guess that the worst case scenario is O of n squared, because you're seeing the worst possible nightmare case where the while loop fires all the time, always, as much as possible, right? If that's the case, then we're looking in this world at what? Type in chat if you know. What's the worst case scenario here? It's the opposite, right? If it was reverse sorted, so in other words, it's sorted in decreasing order, then we're going to look and have a big problem here, because every number we look at has to shift all the way up to the beginning. What that means is that the while loop needs to fire over and over and over again every time we're inserting to the front, right? I want you to really understand the pseudocode. This is saying while j is greater than or equal to 0, so while the index is still valid and the current element is greater than the element we're looking at. If we're looking at a reverse sorted list, the current next will always be, this will always be true. The current next will always be smaller than the current element because it needs to be moved to the beginning. So we have to do the shifting, which is this line. This line represents the element being shifted in green all the way toward the beginning, right? And we'll have to do that every single time. That means the while loop on the inside runs in roughly n over 2 time on average. And there's n iterations of that, which means that it's n squared over 2 overall, which is where the n squared comes from here. Okay, average case is somewhere in between. We're going to go ahead and just say this is n squared and not think too much about it. And this is constant space, because all we did was we defined next, we defined an index, we defined j, but we didn't create any new lists, right? And as I made you all type before, the size of the input does not count when we're considering space complexity. We don't consider the input when we're trying to compute the space complexity. It's only any new space that's being used. All right. Let's go ahead at this point, take a 2-minute break. It's not 5 minutes because I got 10 minutes to teach you the basics of quicksort. Hopefully all of you have seen quicksort at least once before. We're going to take 2 minutes. What was the best runtime? O of n when we have the sorted list, because then the while loop doesn't fire in the middle, and the while loop is kind of the important bit. All right, 2-minute break, but I also wanted to show you the announcements for today. So you're really just taking this time to not think about code. Let's think about announcements real quick. Quiz is next Wednesday for you all, or Thursday. It's Thursday for everyone live. It's Wednesday for anyone from Monday. It's going to cover runtime, big O, big omega, and big theta. So stuff we're going to talk about, or what we've been talking about. You can go to this Piazza post to go and try out some of the practice. And the logistics, as always, are described here. So if you've never taken a quiz before, first you should send me an email to see if you can make up some of the other quizzes. Second, you should read this Piazza post to make sure you understand how the logistics work. Homework 1 is due Thursday before 11:59 p.m., right? Or it's due at 11:59 p.m. There is a clarification that you should read up on if you haven't already. And there's some help from the homework party. The video is already linked here. And if you need help on submitting it, you need to check out the intro video. There's some resources on how to learn Java and data structures. If you haven't looked at those before, they're linked here. Homework grade and quiz grades are being worked on right now. Quiz 0 is pretty much almost released. Almost everyone has their quiz 0 grade. Quiz 1 is going to be released next, and homework 0 should be released by the end of this week. And then extra credit will be if you fill out the survey that hopefully everyone got. It should be called Facebook Pre-Course Survey Spring 2021, and it's sent to your GSLU email. You should ignore the first email you got. The second email is actually correct. It's anonymous. No one will read exactly who you are and your answers. They're not going to be associated. This is only here to help us figure out who's in the class and what you've learned in the past and what your background is like, so that we can understand more about who's in the class and how we're helping them, right? This is really helpful for us because we really want to make a difference in our classes, and knowing who's in the class helps us answer that question of whether or not we're actually making a difference. If 85% of the class complete the survey on time, everyone will receive 1 point of extra credit on the first exam. If 90% of the people complete the survey on time, then they'll receive 2 points. And then if 95% of the class complete the survey on time, everyone will receive 3 points, which is actually quite a lot. It's like 1 point of your final grade. All right, let's go ahead and move on. What if it's 100%? If it's 100%, I'll dye my hair. I'll bleach my hair pink and dye it. I'll bleach my hair and then dye it pink. I've never seen 100% in all of my years of teaching. All right, so let's go ahead and take a deep breath. Type quick in chat if you're ready to learn about quicksort. All right, type sort in chat if you've seen quicksort before, and type anything else if you haven't seen quicksort before. Okay, most people have seen quicksort before, and some of you didn't fully get it. It's going to be mostly a review. We're going to spend some time on it next lecture since we only have about 10 minutes now. But basically, the intuition is this, right? Quicksort is the least intuitive of all of the runtimes, of all of the n-squared sorts. But it's actually the most useful. It's used in real life a lot. There's a lot of programming languages that have built-in sorts that are similar to what quicksort actually does, right? It has some flavor of quicksort inside of it. We're going to go and pick the last element in the list, right? We're just going to pick a number from the list. That's going to be our pivot. We're going to use that pivot to put the rest of the elements into 2 smaller lists. The first list is everything that's smaller than or equal to the pivot. The second one is all the elements that are greater than the pivot. And then we're going to recursively do the same things to the smaller lists, right? So we'll pick a pivot for each of the smaller lists. We're going to break that smaller list into 2 even smaller lists, and then keep going all the way down. Once we've sorted the smaller list, we're going to glue them back together at each level, and then we're going to glue them along with the pivot, which is like the end of the, like that's it. That's the entire algorithm, right? So you might not understand exactly what I mean by that. I'm just going to go through an example here. Here is a list. You can see that it has different colored 5s because we're going to try to answer the question of stability if we have time. And then we pick 3 as the first pivot. I'm going to give you 5 seconds. What are all the elements that go in the left partition? What I mean is that there's going to be a list, and that list contains in order all the elements from left to right that are smaller than 3. Go ahead and type in chat if you have it. What is the list? Should be 2 and then 0. Skip all of these since they're bigger than 3, and then the other 2, and then the 1, right? That's exactly what we have. 2021. Huh. Anyways, moving on. We'll do the 3 on its own thing, right? And then we'll have all the other elements that are bigger than 3 on the right in this own list, right? Then we do the left-hand list and do the exact same procedure where we pick 1, and then we split all the elements that are smaller than 1 on the left, which is only 0 in its own list right now. Bring down the 1, that's something we'll need to combine, and then bring down the 2 2s, right? How about on the right? We don't go on to the right-hand side yet. We keep going recursively deeper. We pick 2 as the pivot, we sort the other 2 onto the left, and then we have 2 here. At this point, we're actually allowed to combine. We take these 2 2s and glue them together. We have 2, 2, right? That's considered quote unquote sorted, which means coming out onto this level, we're going to glue the 0 together with the 1 with the 2 2s that we have. All right, that's what we have so far. Type in 0 1 2 2 if you feel like you understand the procedure as it is. And then you can like type a question mark or anything else if you're confused. Okay, most people feel like they know what's going on. And quicksort's not scary. You can go and watch a video on this where they'll explain it a little bit more in detail if you're confused. And you can also book an office hours, and I'll be happy to walk through this in more time. But right now we have 5 minutes, so I have to move a little bit faster. So moving on. Now we have to do the right-hand side. The base case is basically when the list is like of length 1 or length 0. You'll see in the next slide exactly what I mean. we take the 6, we put everything that's smaller than the 6 on the left. In this case, it's the 2 5s. 6 comes down on its own, and then everything that's to the right of the 6 comes down in order as well, right? You see that I'm not sorting the 9 and the 7. I'm just bringing it down and like arranging it so that it's in its own list on the right hand side because it's larger than 6. Then we handle the 5s. The 5s get glued together in order, right? You can see here that the answer to whether or not this is stable is already being given here, right? Red 5, blue 5, which is probably confusing because the text is red. Anyways, we also do the right hand side. We pick the 7. We know that the 9 goes to the right of it, and then we glue that together as well. So then we know that on this side we have 7, 9. And then on the level above, when we're gluing all of this together, then we go ahead and say that we have red 5, blue 5, 6, 7, 9. It's almost a rhyme. And then on the top level, we finally have here, if I can get my text tool back, 0, 1, 2, 2, red 5, blue 5, 6, 7, 9, right? And that's just gluing everything together, right? So this is an example, small example. We're going to go ahead and take a very brief look. Am I missing a 3? I'm missing the 3. Thank you. People in chat are typing 3 in chat because I missed a 3 here. I forgot to glue the pivot together. Nice. And then some people are typing 3 because they think they're supposed to. All right. So let's go ahead and take a look at the pseudocode now. Right? Pseudocode here says this. If the length of the list is smaller than 2, whether it's an empty list or a list with only one element, we just return the list itself. Otherwise, we're going to pick a pivot. We're going to create a new left list and a new right list and iterate through from 0 all the way to n minus 2 and just add all of the elements that are smaller or equal to the pivot to the left list. Otherwise, throw them into the right list and then recursively call on the left, glue that together with a pivot, and then recursively call on the right. Now, this one thing that I need to note here is that plus here means list concatenation. Right? You don't have this in Java. What you need instead is like add all or like some other like language construct. You don't actually have this plus. You can't add lists or arrays together with plus. But in pseudocode, we can do anything. So this is just making it a little bit more readable. I believe add all is the right element that we care about here. And again, we're going to go ahead and spend about 1 minute just identifying all of the different parts here. So we have these parts of the list of procedures in white, like the big idea in white here that I want you to try to map to the code, right? For the first one here, what is the line in code that I should be highlighting to say that this is the big idea and it corresponds to this line in code? Type it in chat if you have it. Where do we pick the last element in the list? Like, where do we pick the pivot here? It's the third line. In other words, pivot is equal to list of n minus 1, right? Hopefully that's not too scary. How about this part? When we say put the rest of the list into 2 partitions. What do you think what do I highlight in red here? Everything else. Yeah, the code here, all of this is the red part. You can see how the red part, typing it out in words is a lot easier than actually writing the code out. We have to create 2 new empty lists, iterate through from 0 all the way to n minus 2 because n minus 1 is the empty. We already picked the pivot, so we don't have to deal with that one more time. And then add the elements at each stage into the list itself. Like either into the left list or the right list. All right, I'm going to keep moving a little bit faster now. We know we're going to have some recursive calls. So the recursive calls are literally just right here, right? Because you can see we call quicksort again on the left and the right. And then lastly, the gluing together that I'll do in purple here is this entire line here. right? This idea, especially the pivots, the adding that we're here, which means that we're taking three different lists and putting them together. All right. Now, I have to keep going because we're out of time. So we're going to skip the runtime. We'll cover that later, and we'll go ahead and talk about the takeaways. Big O, big omega, and big theta provide a means to express the upper, the lower, and the tight bounds. You should never confuse this for worst, best, and average case. Don't get it confused. My cat is being fed. Don't worry. Selection sort provides an intuitive but slow means of sorting elements in place. Insertion sort is slightly less intuitive, but actually better in the best case because it's O of n instead of O of n squared. And then quick sort is the least intuitive of all three. I haven't explained why it's the fastest, but it's actually the fastest in practice. And its best case and average case are just basically really, really good. And there are further optimizations that can be made to turn this into an in-place version, which we'll probably do on a homework or something. When is the survey due? I'm not sure. Probably a week from now. I need to confirm that, and I'll give you an update once I know. Basically, all of these algorithms take n squared in the worst case. And that's all you need to know for today. If you have any questions and concerns, feel free to ask. Otherwise, we're done for today. Please go on Piazza and check out the announcements if you haven't checked them out already. Read them out in more detail. Make sure you follow them all. My cat is very, very good about letting me know when it's time to feed him. It's like he has his own alarm clock. Okay. Thank you for your time. If you have any questions, let me know. Otherwise, I'll catch you next lecture.